Imagine scooping up a single teaspoon of something. Now imagine that tiny amount of material weighs as much as every single building in New York City combined. All of them, stacked on your teaspoon. That is not a metaphor. That is not an exaggeration. That is a neutron star. And once you understand what that actually means, you will never look at matter the same way again. Every atom is mostly empty space. You probably heard that before, but let's actually sit with it for a moment. Your body feels solid. The chair beneath you feels solid. The floor, the walls, your phone in your hand, all of it feels completely solid. Tap the desk in front of you. It feels firm, real, undeniable. But at the atomic level, it is almost entirely nothing. The nucleus at the center of an atom is like a marble placed in the middle of a football stadium. The electrons orbit somewhere near the outer stands. Everything in between? Empty. Void. Nothing. If the atom were the size of a cathedral, the nucleus would be a fly at the center, and the electrons would be dust motes drifting near the walls. If you squeezed all the empty space out of every atom in your body, if you compressed yourself down until there was no gap left between any of your particles, you would fit on the head of a pin. The entire mass of a human being, crushed into a dot smaller than you can see. That sounds impossible, but neutron stars do exactly this. They just do it with an entire star. In 1934, two physicists at the California Institute of Technology changed the way we think about the universe. Walter Baade and Fritz Zwicky were studying what happens when massive stars die, and they made a prediction so strange that most of their colleagues did not take it seriously. They said that when a giant star collapses in a supernova, when it explodes and throws its outer layers into space, the core that remains could be compressed into something almost unimaginably dense. A ball of matter so heavy and so compact that nothing in everyday experience could prepare you for what it would feel like. They called it a neutron star. The name comes from the way it is built. Under normal conditions, atoms are held apart by the forces between protons and electrons. The electron cloud around each atom prevents the atoms from touching. But in a neutron star, the pressure is so extreme that protons and electrons are crushed together to form neutrons. The fundamental equation is simple. Proton plus electron equals neutron, releasing a tiny particle called a neutrino that escapes into space. Every atom is dismantled. Every electron is squeezed out. What remains is a ball made almost entirely of neutrons, packed as tightly as they can physically be packed. It took another 33 years before anyone found one. In 1967, a graduate student named Jocelyn Bell Burnell was working at the Mullard Radio Astronomy Observatory in Cambridge, England. She was using a radio telescope she had helped build, a massive array of over 2,000 dipole antennas, stretching across an area the size of 2 tennis courts, and she was scanning the sky for something completely different. She was looking for quasars, not dead stars. But she noticed something peculiar, a signal, a pulse, coming from the same fixed point in the sky in the constellation of Vulpecula, ticking with the precision of a clock, once every 1.33 seconds. At first, her team could not explain it. Radio signals from space are common, but this was different. It was too regular, too precise. Someone half-jokedly labeled it LGM-1, standing for Little Green Men, because the signal was so exact it almost looked like it could be a message from an intelligent civilization. But it was not aliens. It was a pulsar, a spinning neutron star lighthouse beaming radio waves across the universe. Neutron stars have incredibly strong magnetic fields, trillions of times stronger than Earth's, and those magnetic fields funnel beams of radiation out of the poles. As the star spins, the beam sweeps across space. When it points at Earth, our telescopes pick up a pulse, a cosmic heartbeat. Jocelyn Bell Burnell had found the first one. The discovery would win the 1974 Nobel Prize in Physics. The prize went to her supervisor, Anthony Hewish. Bell Burnell was not included. But in 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million, and donated the entire amount to fund scholarships for underrepresented students in physics. Today, we know of more than 3,000 neutron stars, and the numbers attached to them are the kind your brain simply refuses to process. A neutron star is roughly 20 kilometers across. That is about 12 miles. You could drive across one in less than 15 minutes. It is roughly the size of a city, somewhere like London or Houston or Beijing. But it has the mass of 1.5 to 2 suns. Your sun weighs about 330,000 times the mass of Earth. Earth itself weighs about 6 sextillion tons. That is a 6 followed by 21 zeros. So imagine something 330,000 times heavier than everything you have ever known. Every ocean, every mountain, every person, every grain of sand on every beach on Earth, squeezed into a ball the width of Manhattan. 1 teaspoon of that material, if you could somehow scoop it up, would weigh approximately 6 billion tons. 6 billion tons. That is roughly the mass of every man-made structure in New York City, stacked onto a spoon the size of your pinky fingernail. If you dropped it, it would not float gently to the ground. It would crash through everything beneath it, through your hand, through the table, through the floor, through layers of concrete and steel and earth, sinking toward the center of the planet like a bowling ball falling through fog. It would pass through the Earth's crust, through the mantle, through the liquid outer core, and settle somewhere near the center. The surface gravity of a neutron star is about 2 billion times stronger than Earth's gravity. If you stood on the surface, and you absolutely could not survive this, you would be instantly compressed into a layer of atoms less than a millimeter tall. A person would become a thin smear on the ground. A marshmallow dropped from a meter above the surface would arrive with the kinetic energy of a small nuclear bomb. These are not theoretical fantasies or artistic exaggerations. We have observed them directly. In 2017, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, along with its European counterpart Virgo, detected something extraordinary. 2 neutron stars spiraling toward each other, locked in a death spiral, accelerating as they fell together. They merged. They collided. The event, labeled GW170817, was the first time a neutron-star merger was observed in both gravitational waves and in light, across the entire electromagnetic spectrum. Over 70 telescopes around the world and in orbit turned to watch, and what they saw was astonishing. The collision produced a kilonova, an explosion so powerful that it forged elements heavier than iron, elements like gold, platinum, and uranium. Scientists calculated that GW170817 produced an estimated 10 Earth masses worth of gold alone. 10 Earths, made of gold, in a single collision that lasted less than a minute. The jewelry on your finger, the gold in your electronics, the platinum in your catalytic converter, all of it may have been forged in the death of neutron stars billions of years ago, long before our sun even existed. But here is the part that should genuinely unsettle you. A neutron star is matter at its absolute limit. It is the densest form of matter that can still exist as matter, and there is a ceiling. If a neutron star exceeds about 2.1 times the mass of our sun, the neutrons can no longer hold. The internal pressure, called neutron degeneracy pressure, which is the quantum mechanical force that keeps neutrons from occupying the same space, is overwhelmed by gravity. The star crushes past the point of even neutron density, past the point of anything we fully understand, and becomes a black hole. In 1939, J. Robert Oppenheimer, the same man who would later lead the Manhattan Project and build the first atomic bomb, published a landmark paper with his student George Volkoff. They calculated this exact limit. They showed mathematically that there is a boundary, now called the Tolman-Oppenheimer-Volkoff limit, beyond which neutron matter cannot support itself against gravitational collapse. Beyond that line, collapse is total and permanent. There is no coming back. 2 years later, Oppenheimer and another student, Hartland Snyder, published the first paper to describe what actually happens during gravitational collapse, the formation of what we now call a black hole. Oppenheimer was not just a weapons physicist. He was, for a brief window, one of the most important theoretical astrophysicists alive. So when you hold that teaspoon of neutron star material in your mind, you are holding the edge of known physics, the densest thing that can still be called matter. 1 teaspoon, 6 billion tons, a city's weight in a spoonful, and if there were just a little more, just slightly heavier, it would no longer be matter at all. It would become the one thing in the universe from which nothing escapes, not even light. Your body is 99.9999999% empty space. The chair holding you up right now is almost entirely nothing. The floor beneath your feet is a lattice of emptiness held together by forces so small they do not even have mass. The reason you do not fall through is not because the floor is solid. It is because of the electromagnetic repulsion between the electrons in your atoms and the electrons in the floor's atoms. You are not sitting on anything solid. You are floating on a field of repulsion, hovering over a void, barely separated from the emptiness below by the smallest possible distance. A neutron star removes all that empty space. It takes the polite fiction of solid matter and crushes it until it becomes honest. The next time something feels heavy, a suitcase, a deadline, a difficult conversation, a responsibility, remember that weight is just a story about gravity and the space between your particles and the ground beneath you. It is electromagnetic resistance pretending to be solidity. And somewhere out there, in the collapsed wreckage of a dead star, there is a teaspoon of something that makes everything you have ever lifted feel weightless. 6 billion tons in a spoon. The universe is not just bigger than you think, it is denser.